I'm Katelyn.
I'm Colm.
I'm Sam.
And I'm Maury.
And
we're Team 9.
Our project this semester was Sharks and Minnows.
Woo.
Because we're recreating a Sharks and Minnows game, we decided to use 2 minnows and a shark as our players. We'll also have up to 5 obstacles on the field that our players must avoid. They also need to stay within the bounds of our playing field, which is 120 by 180 centimeters. The game will end when either of the minnows is tagged by the shark, or one of the minnows reaches the finish line.
A tag is considered to be when the shark is within 8 centimeters from a minnow. The shark will only target one minnow at a time, and the obstacles will be circular and around 20 centimeters in diameter. A rover should never hit an obstacle. Our shark has a slight disadvantage. It can't see where the obstacles are located. It'll detect them when it gets very close to them and add the obstacle's location to its memory. It will know the minnows' locations, though, and will try to intercept them on their way to the finish line. The minnows, however, will know the location of the shark, the other minnow, and all obstacles. They will be calculating the shortest path to the finish line while trying to avoid the shark.
Our overall design consists very generally of 3 autonomous rovers controlled by PIC32 microcontrollers, an overhead object detecting camera called a PixieCam to report locations and angles of objects on the field, a finish line monitor which accurately determines when a minnow wins the game, an orientation beacon to provide more accurate and immediate orientation data for all rovers, and finally a central server built on a Raspberry Pi using a basic Python server called Flask. The server was key for allowing communication between all the different components of the system as well as for debugging purposes.
Hi, my name is Sam, and I worked on rover hardware and rover movement. So the initial requirements for the rover hardware and movement are that the rovers must take in a series of XY coordinates generated by the pathfinding algorithms and move through those points while keeping track of their position and orientation. Also, the rovers must have mounted distance sensors to detect obstacles in front of them. They must have mounted IR receivers to determine their orientation relative to an IR beacon, which is positioned near the finish line. And at the finish line, there must be a laser pointed at a photoresistor, which is hooked up to a PIC, and the PIC uses the photoresistor to know when the laser line is broken, which means that a rover has crossed the finish line. In our final design, the rovers are able to successfully take in a series of XY coordinates from the pathfinding algorithms and navigate through the points successfully while keeping track of where they are and how they're oriented. For the distance sensors, though we were able to get them working in isolation, we did that too close to the deadline and we were unable to integrate them successfully with the pathfinding algorithms. So currently in our final design, the distance sensors are not used. The IR beacon and receivers were not implemented in time, and the task of orienting the rovers was instead left to just the motor encoder data and the Pixie camera. Lastly, the finish line PIC was not implemented in time, so we just used data from the Pixie camera to determine when the rovers reached that point of the playing field.
Hi, my name is Colm and I worked on the software for the Shark rover. When we started the project, the Shark rover had 3 main requirements. It should be able to intercept the nearest minnow before either minnow reaches the finish line. It should be blind of obstacles and that it doesn't know where they are initially. This was chosen as a handicap to ensure the shark would not always win. And lastly, the shark needed to signal the end of the game if a minnow was tagged. To meet these requirements, we decided that we would use PixieCam and motor encoder data to determine the positioning and would rely on distance sensors and beacon sensors to validate obstacle avoidance and angle calculation respectively. It would then compute a path to the minnows using a modified A-star algorithm to find a path to the nearest of the 2 minnows. Finally, to counter the shark's blindness, we chose to use 2 distance sensors, which would be used to find objects and build a map of perceived obstacles to avoid. For our final implementation, the shark was able to successfully navigate the playing field, avoiding obstacles and progressing towards the minnows, alerting when it had captured one. However, while we were able to build a map of obstacles using simulated distance data, due to certain limitations, we were not able to fully implement the obstacle building using actual distance sensors reliably enough to be used in the final demonstration. Instead, we removed this handicap and allowed the shark to see the same pixie data as the minnows. Here is an example of a game in which the shark wins. The shark in this case starts at the finish line area, which puts it at a slight advantage. You can see that once all the rovers have received location data of all the obstacles and rovers, they begin to follow a computed path. You can see the shark readjusts to its path as it knows the minnow's location changing, with the run concluding with the shark lighting up all of its LEDs to signal that it has reached a point which is around 8 centimeters or less from the minnow, representing a tag.
Hi, my name's Katelyn, and I worked on the minnow software. The goal of the minnows was to cross the finish line at any point along the width of the playing field. They used map data collected by the Pixie Cam to determine the locations of the obstacles, the other minnow, and the shark. The minnows were originally planned to use a modified version of an A-star algorithm. An A-star algorithm combines the cost of the path and the heuristic to determine the best path, and it tends to choose the best move to make immediately, not necessarily what would be best for the future. Our final design implemented a depth-first search to determine the best path. It was still based off of a grid system using 10 by 10 centimeter grid squares. This gave the most direct path to anywhere along the finish line, while also making moves to avoid obstacles a few grid squares in advance. I also wrote a client that would display the current calculated path of both rovers, as well as the locations of every obstacle. The grid displayed here was an early implementation that only showed Minnow 1's path. Now here's a video of a minnow reaching the finish line. It will turn both LEDs on when it's done. The minnow at the top of the screen is driving towards the finish line. Once it believes it's crossed the finish line and reached its goal, both LEDs will turn on.
The only requirement for the overhead camera was to provide location information for each object on the field to an accuracy of within 8 centimeters. As a redundant check of the orientation data from the IR beacon, the overhead camera was also required to provide the location data for the head and tail of each rover for later calculation of orientation. A Pixie Cam was used for the overhead camera due to its off-the-shelf ability to visually identify and locate objects by color. In an effort to allow for operation under a wider range of lighting conditions, we used illuminated LEDs instead of traditional colored tiles to mark objects of interest. Since the LEDs would cause overexposure on the camera, only a single color of light could be used. To differentiate between objects, the LEDs were flashed at different rates over a period of time, as shown in the table. The Pixie camera captured frames at a rate of 50 times each second, and a full round to determine the location of each LED would take 1500 milliseconds, or 75 frames. Boundary markers placed on the periphery of the 120 by 180 centimeter field were used to convert the X and Y locations of each object from pixels, which were received by the Pixie camera over UART, into centimeters. The final implementation of the overhead camera successfully reported the locations of each object on the field to an accuracy of less than 8 centimeters. The picture on the far left shows the setup of a playing field during a game. You can see that some of the LEDs on the rovers, obstacles, and boundaries are illuminated. The image in the middle displays the raw data that's received from the Pixie camera. Each illuminated LED is reported with its X and Y coordinates for each frame. The image on the far right is a visualization of the data that's reported to the server. You can see that all of the objects on the field, the 2 obstacles and the 3 rovers, have been successfully reported and are available for the rovers to use to calculate their paths. The shark is represented in red, minnow 1 is green, and minnow 2 is blue. The darker squares indicate the tails of the rovers, while the lighter colors are the heads. The 2 obstacles are in purple.
We added a few features to try to mitigate the amount of errors related to rover movement. The shark compared its motor encoder values to the Pixie data to make sure the location was accurate. If there was too much of a difference between the 2 values, the rover would stop moving and wait for more accurate data. The minnow added a weight to the borders of the playing field to encourage it to stay away from the edges. Both rovers would not compute a path unless they received location information for the head and tail of every rover from the Pixie cam. Both rovers also added a buffer area around obstacles to minimize the chance of collisions.
Several error mitigation strategies were used to provide the best data from the overhead camera. Stationary objects, including the boundaries and obstacles, were found first, and their locations were locked in the server. This was done to prevent these objects from bouncing or being incorrectly reported as moving around the playing field. Flash rates seen at multiple locations were ignored, as each rate should only appear no more than once on the field. Steady-state flash rates were also avoided to reduce the likelihood of environmental lighting conditions, glares, and reflections having an impact on reported locations. And lastly, the positions of moving objects were reported to the server with their last known coordinates to provide the most accurate and up-to-date information.
There was a limited ability to function without location data provided by the Pixie. If the Pixie data was out of date, the minnows may not try to avoid the shark at the right time. They'll still be following an earlier version of the path, and they may expect the shark to be much farther away. The shark may never tag a minnow if its Pixie data is delayed as well, because it has no way to verify it's within 8 centimeters of a minnow. And finally, the Pixie only looks for the obstacle locations when the field is initially set up. If it doesn't see an obstacle, it will just assume it doesn't exist because we can have up to 5 obstacles, and therefore the rovers may run into them without realizing they're there.
To increase the robustness of our system, we would need to develop new solutions to some of the problems we faced in different operating environments. We attempted to mitigate these issues by using the LEDs with the Pixie cam rather than color codes, but we still had to recalibrate the Pixie to the floor color, and higher lighted environments tended to cause a drop in Pixie cam's ability to distinguish individual LEDs, while lower light conditions had much better results. Also, we would need to adapt to working in different environments such as carpet, which made our rover slightly slower and caused our location data based on encoder ticks to be less reliable.
We had a few reliability issues. The first is that the Pixie cam had a limited ability to provide real-time location data to the moving rovers. Due to the long cycle times, the Pixie camera was not always able to accurately track the rovers as they moved on the field. Stationary and slow-moving objects were reported with the greatest accuracy, which is why we made our rovers move as slowly as they did. Because the rovers depend on the Pixie cam data to determine paths, if the Pixie cam missed something in a cycle, the rovers would sometimes freeze up as they waited for the next cycle of data to come. This visibility issue is mostly due to the fact that the LEDs we were using had narrow fields of view and were difficult to identify when located near the periphery of the field. We ended up with 3 LEDs on each marker to increase the field of view, but there were still some cases where the Pixie cam had a difficult time identifying the illuminated LEDs around the edges of the field. Lastly, the slight delay between getting orientation information about the rovers from the Pixie cam and sending that information to the rovers meant that the rovers were sometimes a little off of where they thought they were, by a few degrees. But when rotating and then moving forward, a few degrees of inaccuracy on the rotation causes much more inaccuracy at the end of the forward movement. We could have done a couple things better to better meet our requirements. The first is better tag and finish line detection. In our final demonstration, both of these depended entirely upon the Pixie cam, and to be more accurate, we could have used distance sensors in the case of a tag, and the laser line breaking pick in the case of finish line crossing. To start and stop all the rovers at the same time, we could have implemented a game start signal that is sent to all rovers to start the game, and a game over signal that is sent to all the rovers when a minnow wins or when a shark tags. Lastly, we could have implemented a GUI to show the score and to manage starting and stopping more easily.
In a future system, in order to increase the reliability of the location information, I would recommend using LEDs with wider fields of view to be better seen by the overhead camera. I would also suggest that additional sensors are used to add redundancy when determining the location of each rover as it moves across the field. I would also look to reduce the flash rate cycle times as much as possible. Since this would likely reduce the accuracy of the data from the overhead camera, the pathfinding algorithms would likely have to be modified to better handle inaccurate or missing object data.
There you go.
We're going to keep that.